All right, so we're talking about rational functions, which have to do with polynomials divided by polynomials, right? And one of the things that we left off in our last class meeting talking about was vertical asymptotes, right? And so what we did was we looked at our function f of x equals the function 1 over x, our reciprocal function, and we tried to determine what happens to our y values as our x approaches our 0 value from the left. That's on this side of our graph. As x approaches 0, approaching 0 from the left is on this side. Our function is here. Notice our function will continuously go down, and so we'll say that f of x approaches negative infinity. And from the right, our function will go up continuously as x approaches 0 from the right. We're going this way, and our function is going up continuously, and so we'd say positive infinity. And what we said last time was when our function approaches a distinct value, right, from the left and or the right, and I get an infinite value, infinity or negative infinity, that means we have a vertical asymptote. Asymptote, right? And so here, the line that represents this distinct value is our vertical asymptote. All right, this is a line, so I'm going to write it as an equation. Vertical lines come into form x equals some value, and the value that we were approaching in order for y values to approach positive and negative infinity was the line x equals 0. And so we're going to say x equals 0 is our vertical asymptote. Notice it's not just an x value, it is the line x equals 0. This is how it looks on a graph. If we want to find it analytically, what we can do is we can factor our numerator and denominator and cancel any common factors if possible, right? We were looking at the example f of x equals x plus 2 over x squared minus 4 in class. What I said was, okay, well, some things, the places where we have a vertical asymptote are going to look a certain way when we have the formula for our function here. Notice here, if I factor and I cancel a common factor in this function here, I'd end up with the equation 1 over x minus 2. Now, when we found the domain of this function, we said that the domain will be found for just looking at the denominator and nothing else and setting it equal to 0 and seeing what values, right? So we don't want x to equal negative 2. And from this one right here, and from this factor in the denominator here, we don't want x to equal positive 2, right? In much of the same way, the domain of this function, we don't want x to equal 0, right? When x was equal to 0, we had a vertical asymptote here, right? Well, not all places where our denominator equals 0 causes a vertical asymptote. It is only the factors that do not cancel that cause a vertical asymptote to occur. So I'm going to go through the process of factoring my polynomial, and I'm going to cancel my common factors. Then whatever denominator I have left, I solve this equation for 0, and that's going to give me my vertical asymptote. So I have a vertical asymptote, I'm going to say VA, at the value that's not in the domain that doesn't cancel with my common factor. The values in my domain that do cancel with the common factor, these create holes in the graph. So there's a hole in my graph at x equals negative 2, while there's a vertical asymptote in my graph at x equals 2. Right? And so the process of finding our vertical asymptotes, we're going to factor the numerator and the denominator and cancel our common factors if possible. We're going to set the denominator equal to 0 after we've canceled the common factors, and then we're going to solve for x. That is the process we're going to take to find vertical asymptotes. Let's talk about other graphical features for rational functions. Okay, now instead of looking at, and then again we have f of x equals 1 over x. Instead of looking at as x approaches a distinct value, we're going to look at as x approaches positive or negative infinity, right? This is very similar to when we were looking at polynomials and we were considering the end behavior of the function, right? What happens on the right and left side of the graph, right? As x approaches negative infinity, x values going to negative infinity are over here. Nope. If I want to figure out what my y values are doing, I'm going to get on my function and see where my y values are going. My y values are getting closer and closer to my x-axis, very close to my x-axis. And when I approach my x-axis, that is the line y equals 0, right? All the points on my x-axis have a y value of 0. So I'm going to say f of x approaches 0, okay? If I look to the right-hand side, that means as x approaches positive infinity, on my x-axis, x values get large over here. And I get on my function and I want to ride my line as it goes to positive infinity. Notice here, they're above my x-axis, but they're approaching my x-axis as well, right? And remember, all points on your x-axis have a y value of 0, so your y values approach 0, okay? Notice here, I'm approaching infinity or negative infinity for x, and my y values are approaching a distinct value. Okay, when this is the case, we have horizontal asymptotes. Okay, and the horizontal line, or the value of y that your x's are approaching, or your y's are approaching as x approaches negative infinity and positive infinity. That line, it is a line, so I'm gonna make it a line, and I dash it because it's a feature of a graph. It's not actually the graph, but it is a feature of your graph. That line, y equals 0, is a horizontal asymptote. I'm going to abbreviate that with HA, okay? And definition-wise, it says the line y equals A is a horizontal asymptote P if as x approaches a if f of x approaches a distinct value, right? A distinct value as x approaches infinity, or as x approaches negative infinity. If that is the case, we're going to have a horizontal asymptote. Okay, this is what it looks like graphically. There are a lot of things that's going on behind the scenes here, and so I'm going to look at a couple of functions to help us out here to see what's happening behind the scenes here. I have a function here, f of x equals x squared minus 3x minus 4. And if I want to find the horizontal asymptote, what I'm going to do is I want to find what happens as x approaches plus or minus infinity, right? One thing that helps is to divide by the largest power of x in your numerator and denominator. Okay, so if I look at the numerator and the denominator, in this example here, the largest power of x is 3, right? So I'm going to divide both sides, or not both sides, the top and the bottom, the numerator and the denominator, by x cubed. When I do that, now this is going to look a little messy, but each of these terms in the numerator are going to be divided by x cubed. So I'm going to have an x squared over x cubed, minus a 3x over x cubed, minus a 4 over x cubed. Then I'm going to go to my denominator and divide that by all the terms by x cubed. And I'm going to write this out, and then I'm going to simplify. 3x squared over x cubed minus 4x over x cubed minus 6 over x cubed, right? Now I'm going to simplify. Notice I have x squared over x cubed, right? 2 of those x's on the numerator and 2 of the x's on the denominator cancel, and I'm going to be left with a 1 over x. In the second term here, 1x on the numerator and 1x on the denominator cancel. So I'm going to have a minus 3 over x squared. Nothing cancels in that last term. So I'm left with that 4x cubed. X cubed over x cubed is 1. 2 of the x's multiplied on the numerator and denominator cancel. So I have a 3 over x minus a 4 over x squared minus 6 over x cubed, right? Now that I have that, I want to figure out what happens to f of x, because this is still f of x. I just simplified it by multiplying or dividing the numerator and denominator by x cubed, right? It looks differently, but this is still f of x, right? I changed it a little bit. Changed f of x, right? But what I want to do is I want to see what happens to f of x as x approaches infinity, okay? Well, let's look at this one thing here. We've already found that as x approaches infinity for the function 1 over x, we end up with, if you go back to this page right here, as x approaches infinity, our y values get closer and closer to 0. So I know that this term right here goes to 0, right? Well, if I have 3 over x squared, and if 1 over x goes to 0, that means I divide 1 by a really big number. If I divide 3 by a really big number, like 3 divided by 1,000,000 squared, right, that's going to go to 0. And this term is going to go to 0. And all of these terms with an x in the denominator are going to approach 0. And so as x approaches infinity, this f of x here is going to approach, well, the numerator is all 0 plus 0 plus 0, which is 0, over 1 plus 0 plus 0 plus 0, which is 1. Our f of x approaches 0. I can do the same thing with this g of x right here, but this time I have my denominator and my numerator divided by the highest power of x, which is x squared. Okay, I'm going to change colors here. If I divide this by x squared, and if I divide that by x squared, I'm going to have 3 plus 1 over x squared, right? If I divide this by x squared is going to cancel. I'm going to have a 2 minus a 3 over x plus a 7 over x squared. Now I'm going to let x approach infinity, or negative infinity, and we're going to see that this is going to go to 0, this term is going to go to 0, and this term is going to go to 0. And so we're going to be left with f of x. So as x approaches infinity, f of x is going to approach 3 over 2. Okay? So here, when I have this case, x approached 0. When I have this case here, x is approaching 3 over 2. Let's look at one more example. I'm going to have h of x. I'm going to divide the numerator and the denominator by, let's say, the highest power of x is x cubed. And we're dividing here. And so this is going to equal a 1 plus 4 over x plus 7 over x squared minus 2 over x cubed divided by a 1 over x minus a 6 over x squared plus a 3 over x cubed. In a similar fashion as the others, as x approaches infinity, this is going to go to 0, that's going to go to 0, that's going to go to 0. Oh. And so I'm going to have that as x approaches infinity, my function is going to approach, well, I have a 1 plus 0 plus 0 plus 0, which is 1, over, oh, I'd be dividing by 0, right? This is undefined. So as 1 divided by 0, right? And these things are approaching 0. That means this is going to be 1 divided by a really small number, like 0.0000000000001. And when I have a statement like that, my function is going to approach infinity or negative infinity, okay? So it doesn't approach a distinct value, all right? These three cases are going to help me determine what type of horizontal asymptote I'm going to have, right? So as x approaches the end of my graphs, the extreme values of my graph, the extreme size of my graph approaching positive and negative infinity, I'm going to either get 0, some distinct other value other than 0, or it's going to approach infinity or negative infinity, okay? So notice, as x approaches negative infinity, I'm over here, right? And if I approach 0, my function is going to get closer and closer to my x-axis. If I go with positive infinity, it's going to get closer and closer to my x-axis, right? Or I can have this case right here where x is going to approach y is going to approach a distinct value. Sorry, I'm getting tripped up here. So as x approaches infinity, it can approach this line right here, or coming from the bottom, or it can be up here or up here, right? And I can have the case where it approaches positive or negative infinity, which as x goes to the right and my graph is going to positive infinity, so my graph is going to go up here, or if it goes to negative infinity, it's going to go down there, or I'm going to have this situation here or this situation here, right? When this is the case, there is no line that your graph is approaching. There's no horizontal asymptote. All right, but in these two cases, there is a horizontal asymptote, okay? And we'll talk about how to really determine that in the next video.